I think it's been like 2 months since my previous video on solving physics, and yeah, it's been quite a long time. I'm excited to be back, and let's dive right in. Today's question is about obelisks. An obelisk is basically a big rock. It's a rectangular rock that people used in the past, in the ancient times, to build pyramids and all sorts of sculptures. And yeah, it's about obelisks, and today's problem about obelisks is as follows. And the problem is from this book over here, which is Professor Povey's Perplexing Problems. It's a great book. I'm solving quite some questions here in this book, and it's really fun. And so I advise you to try some of these questions on your own. Yeah, let's dive in. Today, the question here that's in this book is as follows. We have an obelisk, a very big one, and its height is L. What we also have is a person who is very small compared to the obelisk, and this person has a rope attached to the obelisk. It's supposed to be straight, but I'm not good at drawing straight lines, but anyways, it's a straight line. And it's connected to the obelisk like that. And the rope also has a length of L. And the problem is, where should the rope be attached to such that the person could most easily put this sculpture down, such that he could use or whatever. Like, this person is trying to use the obelisk, but anyways, the person wants the obelisks to fall with the minimum amount of force, or the minimum amount of torque, or the maximum amount of torque with the same amount of force, such that he could most easily put the obelisk down to the ground. So that's the question. And looking at this question, first of all, on any question, it's best to first draw a force diagram and depict all the forces acting on the system, and evaluate which force is equal to which force must be something such that maybe the net force is 0, and so on. And so let's draw the force diagram. We have the obelisk like that. And yeah, one important thing is that this person, when he, like, the rope and his arms must be horizontal, so or parallel. So when the person is holding the rope like that, the rope should be in parallel to the direction of his arms. So what we could do is depict the person as a perfect rectangle, like as follows, like that, or maybe something a bit narrower, like that. So this is the person, and the person from his arms, this is the person's arms, is holding a rope. It's like that, and this is the point, and we're trying to find which point here would give the maximum torque. And what we know is that, well, there's gravity acting on the center of mass of the person. That's going to be mg. We know that the force the person has got to be it's pulling the rope, so it's exerting a force. The rope would be exerting a force on the arm of the person, because the person is pulling the rope. And so there's the force F that the rope exerts on the person, so the rope is pulling on the person with force F. And there is a force F also equal in magnitude that the rope pulls upon the obelisk, and this force is what causes the obelisk to fall down. And are these the only forces? Well, no, because the person has a feet, obviously, so he's going to have a normal force that acts upon the feet of the person, that the ground acts upon the person, and also there's going to be the force of friction, because the person is trying to, force will try to pull the person towards the front, so there would be a force of friction that the ground exerts on the person, opposite to the direction that the person tries to move. And these are basically all the forces labeled. And so first I'm going to erase that. We have this force diagram over here. Now, what we know, first of all, what we know about the torque here is that the torque will first of all act upon this point here, because the obelisk will be falling down like that. And we also know that let's label that as h. So h is basically what we're trying to find. We're trying to find what value of h gives maximum torque. And so we have to label h. And now what we know is we could say, first of all, that this here is theta. The angle in which the force is directed towards is theta, from the ground. That's theta. And so this angle will also be theta, which means that the horizontal component of this force is F cosine theta. And we know that torque is equal to the product of the distance from the pivot point and its perpendicular force, the perpendicular component of the force times the perpendicular distance would be h, which means that torque, labeled like that, is going to be equal to F cosine theta times h, so Fh cosine of theta. That's going to be our expression for the torque. And what we also know, now looking at the person, is that the person should be in equilibrium. The person may be rotating, so the person may have torque, we don't know. But what we do know is that the person shouldn't be sliding, like he shouldn't be moving up or down or right or left, so the net force acting on the person is 0. So that's what we know, so that's number 1. Number 2 is that the net force is 0. And when net force is 0, we know that let's first of all look at the vertical components of the force. So net force in the y direction, in the vertical direction, is 0, which means that, well, first of all, we have this, which is F sine of theta. That's the opposite sign, same as that. So F sine of theta plus normal force plus this gravity is equal to 0. And the gravity is acting in the opposite direction, so we could say that F sine of theta plus normal force minus mg is equal to 0, which means our normal force can be given as mg minus F sine of theta. That's what we know. And then looking at the horizontal direction, so in the x direction, the sum of the forces in the x direction is also 0, which means that F cosine theta, which is here, F cosine theta must be equal in magnitude to the friction force, because those are the only two horizontal forces. So F friction force is equal to F cosine of theta in magnitude. Now, what do we know about the relationship between the normal force and the friction force? Well, what we know is that the friction force is equal to coefficient of friction times normal force, which means that F cosine of theta, which is the friction force, is equal to mu times the normal force, which is mg mu minus F mu sine of theta, or mu of sine theta, it doesn't really matter. And because now what we want to do is plug our value of F from this equation into our torque, and then determine what value of h optimizes our value of our equation for the torque. And so to do that, we have to rearrange this in terms of F, which is going to be F cosine theta. That's equal to, this expression here is equal to F cosine theta plus mu F sine theta is equal to mg mu, which means that F is equal to mg mu divided by, well, F times cosine theta plus mu sine theta is that, so divide both sides by cosine theta plus mu sine theta, which we have cosine theta plus mu sine theta on the denominator. So our value of F would be as follows. And we have this equation over here, so combining that here, I'm going to label it number 2. Combining number 1 and number 2, we have torque is equal to F times h cosine theta. We have our value for F here, which means mg mu h cosine theta over cosine theta plus mu sine of theta from number 1 and number 2. We're just basically adding h cosine theta to the numerator because we're multiplying. f times h cosine theta. So f here times h cosine theta, that gives our value for our expression for the torque. Now to simplify this, maybe I could divide both sides by cosine, giving us mg mu h over 1 plus mu tangent theta. Now, tangent theta. Before I made an important point about the person's height being negligibly small compared to h or compared to the height of the obelisk, which means that although this diagram here is quite exaggerated, we could say that the person can be considered as a dot. And when we do that, when we consider the person as a dot without any height because it's negligible, we could draw the obelisk like that. And this point is here. So the length of the rope is L, that here is theta, and the height in which the rope is placed is going to be h. And from this diagram, because this is a right angle, we could say that tangent theta is equal to h over this length over here, and that length over here is going to be square root of L squared minus h squared, because due to Pythagorean theorem. So we can say that tangent theta is h over square root of L squared minus h squared. That's going to be our value for tangent theta. Which means that when we plug this equation, this value for tangent theta into the equation, we have our torque is equal to mg mu h over 1 plus mu times tangent theta, which is mu h over square root of L squared minus h squared. That is our equation for the torque. Now what do we want to do with the torque? Well, I said in the question, the question asks us to maximize our value for torque and find the value of h that gives our maximum value of the torque. And so that sounds exactly like an optimization problem where we're going to have to find what value of h gives the derivative of the torque in terms of h equal to 0, because we're finding what value of torque is what value of h maximizes our value of torque. So when we plot a graph for the torque, it's a maximum value, so our derivative at that point is going to have to be equal to 0, which means what we want to do ultimately what we want to do is find what point gives d torque over dh equals 0. That's basically what we're trying to do. So now we have our value for torque. So let's erase everything else and work on the derivative. And hopefully after we do that, we're gonna be able to figure out what the answer is. The value of h that gives maximum value for the torque. So let's write that down again. Torque is equal to mg mu h over 1 plus mu h over square root of L squared minus h squared. And we're trying to find what value of h gives the torque over dh equals 0. Now we have this equation. Let's multiply square root of L squared minus h squared to both sides because we don't want any fractions inside a fraction. So we have, torque is then equal to L squared minus h squared plus mu h over mg mu h times that. Now what we're trying to do now is d torque over dh. This is not going to be that easy. Well, let's just use the quotient rule. That's going to be, well, first of all, we have to square the denominator, which is square root of L squared minus h squared plus mu h squared over, it's going to be quite long. Well, first of all, we differentiate the numerator, and that's going to give us mg mu square root of L squared minus h squared. Well, before we do that, let's find what is the derivative of the square root of L squared minus h squared, because that's going to be used quite a lot when we're dealing with square root of L squared minus h squared. So d of square root of L squared minus h squared in terms of h, well, that's going to be d of L squared minus h squared to the power of 1/2 dh, which is going to be 1/2 times square L squared minus h squared to the power of 1 minus 1/2 times the inside, so applying the chain rule, and we get minus 2h. And that's going to be equal to, well, 1/2 and 2 cancels out, and so only minus h is left on the numerator, and the denominator we have square root of L squared minus h squared. So the derivative of that is that. So applying this, you could say that that's going to be equal to mg mu. First of all, we're still trying to differentiate the numerator, so that times that, we just did that, plus mg mu h, plus mg mu h times the derivative of that, which is that. So plus becomes a minus, and we have minus mg mu h squared, because we have 2h, and over square root of L squared minus h squared. So we have minus mg mu h squared over the square root of L squared minus h squared. Yeah, that's going to be our derivative of the numerator. And then we multiply the denominator as it is, according to the quotient rule. And then what we have to do is subtract that times, subtract the numerator times the derivative of the denominator, which is going to be mg mu h square root of L squared minus h squared times, well, that here we just said that the derivative of the L squared minus h squared square root is that. So we have minus h over square root of L squared minus h squared plus derivative of mu h, we only have mu because we're doing it in terms of h. So that is the full expression for our derivative of the torque in terms of h. So d torque over dh is going to be that. Okay, it's quite long, very complicated, and we don't like being complicated. So what we're going to do, my gut feeling says that we're going to have to substitute this value over here because into some kind of thing called, anything, but I'm just going to say a, because we see that there are lots of instances where this expression comes out. We have that here, here, here. Basically every term has square root of L squared minus h squared in it. And so my educated guess says that I'm just gonna substitute every time L squared minus h squared appears by something called a. And then when we reach our conclusion, we could substitute it back in to find simplify our rather complicated equation over here. So when we do that, we have d torque over dh is equal to a plus mu h squared, because we're substituting by a, and then in the numerator we have mg mu a minus mg mu h squared over a times a plus mu h minus mg mu h a times minus h over a plus mu. That's what we have. And now we have a plus mu h here, a plus mu h here, none here. And what we're trying to find is what value of h gives d torque over dh is 0. So that here is going to be equal to 0. And from that, we could say that, well, first of all, let's first of all divide these into two parts. So we have that's equal to, that's going to be cancelled out, and we're going to only have a plus mu h in the denominator for our first term. So that's going to give us, and then we can also wrap everything by mg mu. We have mg mu times a, mg mu times a minus mg mu times h squared over a, that's a minus, over that cancelled out, and so we only have one a plus mu h in the denominator, and then minus mg mu h a times minus h over a plus mu is equal to 0. And because that minus that is equal to 0, we could know that these two must be equal, and it's not going to be 0. we have that equation, and this is going to be our, this is going to be have to be true such that, so the value of h, whatever that is, must satisfy this expression over here. Now we see that mg mu is occurring in both sides, so divide both sides by mg mu, so cancel it out, and then multiply a plus mu h in both sides, and we're going to have a minus h squared over a times a plus mu h, because we are, multiplying both sides by a plus mu h. Oh wait, there has to be a plus mu h squared here, right? Yeah, mu h squared. And so multiplying both sides by a plus mu h squared, we have a minus h squared over a times a plus mu h to the power of 1, because that was minus 1 here. And that's equal to a times minus h over a plus mu. And now all we have to do, there's going to be HA, right? HA. Because that's canceled out. And yeah, so now I'm just going to expand everything in here. And we're going to have a squared, a squared plus a mu h minus h squared minus mu h cubed over a. That's equal to, a cancels out, so minus h squared plus mu a h. And here we could see that a mu a h, they're same. They're in both sides, and these two are also in both sides, and so they could all be cancelled out. And we have a squared minus mu h cubed over a is equal to 0. Now this here, we could multiply a in both sides and get a cubed minus mu h cubed is 0. And so when we rearrange this in terms of h, we have, mu h cubed is equal to a cubed, so h is equal to a cubed divided by mu and cube root. And that's going to be equal to, cube root of a cubed is equal to a over the cube root of mu, which is mu to the power of 1 over 3. So h is that. But we still haven't solved the question yet, because a is also an expression that contains h. Okay, so we're not quite done yet. So let's erase some parts. So we have, first of all, we have space here. So we have, just divide everything like that. Unless we need some space, so like that. Yeah, so we have h is equal to, from this equation over here, we have h is equal to a, which is square root of L squared minus H squared over mu to the 1/3. And from that we could say, mu to the 1/3 times H is equal to square root of L squared minus H squared. Now this is a good sign, because when we square both sides, we're going to have H squared here and also an H squared over here. So that's a good sign. And so when we do that, we have mu to the 2/3 times h squared is equal to L squared minus H squared. And now it's simple. We just have to, plus H squared in both sides and wrap it by H squared, which is going to give us H squared wrapped by mu to the power of 2/3 plus 1, because we're adding H plus H squared to this side, and so when we wrap H squared by H squared, we have only 1. So H squared times mu to the power of 2/3 plus 1 is going to give us L squared. And that's going to give us H is equal to, first of all, H squared is equal to L squared over mu to the 2/3 plus 1. So H is equal to plus minus of L over the square root of mu 2/3 plus 1. Now, H, when you look at the diagram before, H has to be a positive number. So that's going to be here. It's just going to be a positive. So we have our answer, which is H is equal to L over the square root of mu to the power of 2/3 plus 1. Yeah, that is the answer. The answer for what is the condition, or what's the expression for h in terms of known variables or constants to give our maximum value of torque is going to be here. L is equal to, h is equal to L over square root of 2 over 3 plus 1. And yeah, that is the answer. That's the conclusion of our video. What this expression implies, maybe I'll explore later on. But yeah, for now, that is the answer. And yeah, thank you so much. Please subscribe. Please hit the like button. And yeah, please please be patient for me to upload more videos like this, related to physics or, computer design. Yeah, that's the end of the video. I hope you liked it. Bye bye.